All right, so hopefully on this one, you did the substitution u equals 4x, right? Is that how we do that? U equals, I don't remember how to do this thing. Oh yeah, u equals x over 4, that's what we do. All right. We do u equals x over 4, so then we get 4u equals x, and so that means that 4 du equals dx. All right, so then we can do our substitution. So our integral of 1 over x squared plus 16 dx is equal to 1 over integral of 1 over 4u squared plus 16 times 4 du. And you could probably factor the 4 out right away, so that equals 4 integral of 1 over 16 u squared plus 16 du. So factor out the 1/16th. We could combine it right away and get 1/4. I'll go ahead and write it one more time. 4 times 1/16 integral of 1 over u squared plus 1 du. This one's inverse tangent. Combine these fractions, 1/4 inverse tangent u plus c, and then sub back in the x, 1/4 inverse tangent of x over 4 plus c. All right, so then it's easy enough to recognize what's going on every time is that we take the square root of this number and call that a. All right, the square root of that number is a. So we call this number a squared. And then what's going to end up out here is 1 over a, right? So a equals 4 in this case. So this is going to be 1 over a out here, and this is going to be x over a in there. So you can get your general case that the integral of 1 over x squared plus a squared dx is equal to 1 over a inverse tangent of x over a plus c. So this is the result that we're going to make use of for everything that follows. It's a good one to memorize, actually. There's not a lot of things that are worth memorizing, but this one definitely is. I personally don't memorize it. I remember that when I have x squared plus a squared, there's like something with an inverse tangent, so I just Google that and it'll pop right up, and this will be it. So you want to know that there is an integration formula for this, and that it involves inverse tangent, and there's like a 1 over a in it somewhere, things like that, or just straight up memorize it. That's your choice. Okay, so now we're going to do these problems. It is in the integrating by completing the square practice, which is posted. This is a worksheet. All right, and so there's a little bit more to these ones, and let's just jump into it. So number 2, we got the integral of 12 over x squared plus 8x plus 25 dx. All right, now the features of this integral that direct us to do the technique we're about to do is that the denominator does not factor. If the denominator could factor, then we would use integration by partial fractions. Okay, so our denominator does not factor, and the other indicator is that the numerator is a constant. So if the numerator were a linear function, then we will have another technique to do, which we're going to do later in this very day. All right, if that numerator is, see, we're doing that today too. So the numerator is linear. Okay, if your numerator is constant, then we're going to do this technique called completing the square. So how that works is that, this integral formula that I have here has x squared plus a squared, but it doesn't have an x term. So it doesn't have an x term in it. This does. So what we're going to do is we're going to take that x term and we're going to turn it into an inside function, a linear, in fact, inside function. All right, so what we're going to do is we're going to look at x squared plus 8x plus 25. Let's pull that out and say, you know what that equals? That equals x squared plus 8x plus 16 plus 9. Right? This is 25 is 16 plus 9. Okay, why do I like this? Because this is a perfect square, right? So what I want to say is that this is going to be, I'm going to use a, so we'll call it, because we're using a for something else. So this number is, let's say we call it 2b, right? Then this number is b squared. So essentially what I do, you've done completing the square before. I take half of 8, and then square it. and that gives me 16. That tells me what number to pull out of the 25. All right, so I have that. So then that means that I can write this as x plus 4 squared plus 9. All right, so that x squared plus 8x plus 25 is really x plus 4 squared plus 9. This technique is right here, so it's called completing the square, is doing this. You've probably done it before in Algebra 2 and Pre-Calculus in other contexts. All right, so now I can say that that integral of 12 over x squared plus 8x plus 25 dx is equal to 12 over x plus 4 squared. I don't know why I want to throw out my integral signs all the time now. Dx. All right. Typically, I pull out the 12, although you're gonna see that we can combine that with subsequent steps. X plus 4 squared plus 9. Okay. So then on this one, what I'm going to do is recognize that the integral of 1 over x squared plus 9 is equal to 1/3 inverse tangent of x over 3. Right. That's our formula that we just learned right here using a equals 3. In fact, this is the first example of this that we did. All right. So, but what we're doing here is a linear u substitution where u prime is equal to 1. So we don't even have to do times 1 over u prime. So basically, we'll just sub x plus 4 into this formula. So then I will have 12 times 1/3 inverse tangent of, instead of x over 3, I'm using my u substitution of x plus 4 over 3. And then I have plus c, and boom, that's my antiderivative. All right, so 12 times 1/3, I'll combine that and make it 4, and not much else I can do that's valuable here. And that is the technique of completing the square. So actually, if you get this, it always goes the same. So you can do all of these problems the exact same way. If you want, just do that. I'm going to go ahead and do like maybe one more example or two examples. And then you're going to have odds assigned as homework. And of course, I'm doing the evens as examples.